Okay, sorry this is taking so long. Just read over the notes at the beginning and highlight the words that you need to be able to identify. So far, the techniques that we've looked at have looked at just one molecule, identifying what the molecule is, but this technique looks at separating the substances in a mixture, so a whole lot of molecules together. You can separate them and analyze them individually, so it's a really powerful technique. To do chromatography, you need two parts to your column. So you need something that doesn't move, so the stationary phase does not move. Can be a solid, like beads, or a liquid on beads, and it can range from being totally non-polar to polar, and it can even be charged, so have ions on it. The mobile phase is the solvent that's going to carry your mixture along past the stationary phase, past the parts that don't move. It also is a liquid, so your mixture would be dissolved in this liquid and carried along, or it's a gas, and it can also vary in its polarity and its charge. So different substances in the mixture will dissolve in the mobile phase, in the solvent, and then we say they adsorb, or are attracted to and stopped onto the stationary phase. So as they're being carried along, they will stick to the surface of the parts that aren't moving. And they all do this, different substances will do this at different rates, depending on their attraction to the stationary phase, or physical problems, so if they're the size of them or the shape of them. Then once they're stuck on the stationary phase, then they desorb, come off the stationary phase, and they go back into the mobile phase, and they're carried further along. As different substances will do these processes at different rates, a mixture of substances will become separated. All right. Adsorb and desorb are the nouns, so your adsorption. Adsorb's a verb. Adsorption is a noun. Notice that it's adsorb, not ab with a B, sorb. Okay. All right. So qualitative analysis. So we can do both qualitative and quantitative with chromatography. So we can work out what the chemical is with this technique. So because I've already mentioned, different substances move at different rates. They adsorb and desorb at different amounts, and so this can be used to identify them by comparing them to the known time, or the time, sorry, of a known standard. A chemical that you know, a standard is a chemical that you know what it is. So if you've got a mixture and you don't know what's in there, if you know how long it takes a particular chemical that you know what it is, then if you've got some other chemical that goes exactly at the same time, then you must have that the chemical that you know in your mixture. If you can compare it to the times of known standards, so look up a book, or you could put the standards, the chemicals that you know what they are, you could put them with your mixture and then see if you get more of that particular chemical coming out. Okay, quantitative analysis, quantity, tells you how much there is. So the different amounts of a particular substance, you can work out how much you've got by comparing the area. We'll look at the peak area to a calibration graph. So a calibration graph are standards again, but these standards we know the amount of. They're standards for amount rather than standards for what it is. Okay, this is a video that we watched last year. This is the mixture that we're going to separate, and this is the column that we're going to separate them on. So this is made up of a whole lot of little particles like sand. This is the stationary phase, it's not moving, and so we put our mixture in one end of the column, and then a solvent, so like water or alcohol, some sort of solvent is run through. So it's running through all the time, and it carries your mixture, the molecules through. So you can see that the red chemical, whatever it is, has traveled through faster. So it's more attracted to the mobile phase. The yellow and the blue and the black are doing a lot more adsorbing. So they're attracted to the stationary phase and then they desorb back into the mobile phase. So they adsorb and desorb. So this one is adsorbing, being stuck, attracted to the stationary phase a lot more than all the rest of them. So because they adsorb and desorb at different rates, different amounts, they're more attracted to the stationary phase or less attracted to the stationary phase and more attracted to the mobile phase, then it will separate them. Okay, so if we were to zoom into the little particles in the stationary phase, the little rocks or whatever, and this is our chemical that's moving with the mobile phase, flowing along like in the river, then every now and again it's going to stick onto the rock, adsorb, and then it will be more attracted and carried along by the mobile phase, so it will desorb and be moved further down. Okay, so if this is the stationary phase sticking out like this, rather than just a round surface, then like the shape of the molecules, you can see how the shape is going to affect how fast they move as well. So their attraction, their chemical bonding, and the shape of them. So small, branched, round kind of molecules will move faster than long molecules, like a stick that will get stuck. So round kind of molecules move faster. And if you're not sure about the difference, remember adsorbs with a D, absorb, we've looked at, you can pause it and read the sort of things that mean absorb. Okay, column chromatography is useful. You don't need to write this down. Stationary phase, it's packed, it's in a glass column and you put like sand type thing in it, and then the mobile phase is a liquid or a gas, and we call this, when it comes out, we call it the eluent. So this is a great method like for filtering dirty water or something. You have your column with the stationary phase and then you just pour some water with whatever the mixture is in it, and then it just, gravity just drags it through. And you can see that how long did the red one take to elute? So as soon as you pour it in, we're going to be measuring the time. Okay, the time is going to be useful to work out what it is. And see, the red one's come out first, and then later on the blue one came out. So can you understand why it took longer? It was adsorbed onto the stationary phase. Okay, so that's all very fine if the little particles in here are quite large and the water or whatever it is can just be dragged through by gravity. But we're looking at HPLC and the particles in here are tiny, and the water or whatever the solvent is will never move through just with gravity. So we actually have to put it under pressure and push it through. So when the particles start to come out here, there's a detector. So some method of noticing that molecules are starting to come out, and you have a chart going. So as soon as you put them in here, the chart starts recording and recording the time it takes for the particles to move through. So it's waiting, 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 nothing happens, and then all of a sudden the first particle comes out and you get a peak because it's recorded it. So this is on your sheet. It's like I was saying, we put the chemicals in and we wait. So the x-axis is the time. So the one that is more attracted to the mobile phase is carried through faster, comes out first. And the one that is more adsorbed comes out later. So can you pause this and copy all of this information down? This is a chromatogram that we're going to be analyzing. Qualitative analysis, what it is with this axis. So the time will tell you what it is. So if we look at a standard, if we have put some chemical through, some molecule that we know what it is, through here and it comes out at 15 seconds, and then we put a mixture through where we don't know what sort of chemicals we've got, and we get one that comes out at 15 seconds, then you could say that that chemical is the one that the standard that you knew of before. So the time, that x-axis tells you what it is, and the y-axis, the area, tells you how much. So the more that you have, the larger the area. It would be very tempting to say this one has more than that one, but the area is dependent on the chemical itself. So you would have to compare that chemical to other known amounts of that chemical. Analysis, now we're looking at quantitative analysis. So we've got a series of standards of different concentration. So we plot a calibration graph, which means that we put these chemicals of standards of different concentration through one after another, and we measure the peak area, and then we're going to compare that to our unknown concentration. So this is a calibration graph, and it's peak area versus concentration. So the y-axis is the area, and if the area from the chromatogram is found, then you will measure off the y-axis. And down the bottom here is the concentration. So this line is made by measuring, perhaps you did a standard of 0.1 of some sort of concentration. You put that chemical in the chromatogram, let it run through, and then when you got the peak, you measured the area and found it was 50,000, whatever they're using to measure the area. And then you do another one and you use a 0.2 concentration of something, put it through and measure the area and find it's 100,000. So you do your standards of known concentration, and then you plot your graph. Then once you've got your graph, you put your sample in that you don't know the concentration of. You read the concentration, the area, I should say, the peak area of your peak, and if you found it was 120,000, then you go across to the line and come down, and you'll find that it's 0.2. Need to be able to read the graph. Some of you are not so great with reading graphs, so there's 1, 2, 3, 4, 5 divisions, and this is 0.1, so 5 into 0.1 will be 0.02. So 0.02, 0.04, 0.06, 0.08, and 0.1. So this one is 0.224. So it's 0.24. Okay. So I kept this a bit vague. We don't know what the concentration it is, so it depends on the standards, how you measure the standards. So if we measured them in grams per litre, then your concentration would be 0.24 grams per litre. If we measured them in moles per litre, then it's 0.24 moles per litre. Parts per million, you might remember, is milligrams per litre or micrograms per mil. So this could be parts per million. Could also be percentages. So you always use exactly the same technique, the area of your sample, and measure down and work out the concentration. The only difference is which unit you're using for concentration. Okay, so we're using high pressure liquid chromatography, not column chromatography. Last year we used thin layer, piece of paper, you might remember. So this time we're using high pressure. It's actually high performance, but we're going to pinch the P like we did with the other one and call it pressure, because you're not going to have to remember what the name of it is. HPLC is what we refer to it as. So we'll pinch the P to remember that it's under pressure. And then realize the reason that it's under pressure is that we're using little particles for our stationary phase. And the little particles, the more there are, the more adsorbing and desorbing you do, the better, the more you will separate your mixture. Okay, so we call the time that it takes for your chemical to come out the retention time. So that is qualitative analysis. Oh, I got this. Okay, so the retention time, can you change that? That is to be talking about what it is, not how much. All right. So how long it takes to go through depends on the shape and the attraction that the molecule that you're separating has for the stationary phase and the mobile phase. Okay, so you had to separate these into the chemical that is the most non-polar. So your propane, this one, it's just carbons and hydrogens, similar electronegativity, so the electrons are shared equally, so it's a non-polar molecule. All of the other ones have an OH group, so slightly negative, slightly positive, so they've all got this polar OH group. A and B also have lots of non-polar carbon-hydrogen bonds. The effect of the non-polar chain is the greatest when you've got a straight chain. So this one, which is branched and all sort of clumped together. And also I should mention this should have 4 carbons because we've got 4 carbons. So to compare this one to this one, can you put an extra carbon on your notes? Okay, so the effect of the non-polar chain is greatest in here. So this is more like this one, less polar than that. And so this one, and then that one, and then this one, and then the water. Okay, so can you copy this chromatogram onto your sheet? So we've put chemicals through. Can you see how many chemicals you would have had in your mixture? So you should see there's 1, 2, 3, and a tiny one here. So you've got 4. So reverse phase HPLC is the main one that we're studying. Reverse phase HPLC has a polar solvent, so a polar mobile phase, and a non-polar stationary phase. So if we've got a polar solvent and a non-polar stationary phase, what could you say about the polarity of the molecule at peak A compared to peak B? Okay, so the mobile phase is polar, which means that as soon as the first ones that come out have been carried along faster. So if the mobile phase is polar, then they've been attracted to the mobile phase, so they must be more polar. So this little blip is the most polar, and then the one that comes out the next fastest, B, is the next most polar. And this is less polar, and this is probably the non-polar, the most non-polar, because it's taken longer to come out, so it's adsorbed more to the stationary phase, and the stationary phase was non-polar. Okay, so the substance at peak A has moved through the column more slowly than peak B, so it spent more time adsorbed to the non-polar stationary phase. So you had to write it in terms of peak A compared to peak B. So peak A came out slower, so it has more time adsorbed to the non-polar stationary phase. So if it's spent more time absorbed to the non-polar stationary phase, then it must be less polar, more non-polar, than the substance at peak B. Okay, which would move more quickly through a gas chromatogram? Butane with 4 carbons or pentane with 5. So the smaller it is, the faster it will move, and the more compact it is, the faster it will move. Okay, so we can have a look at that. Qualitative analysis. The unknown compounds can be compared to chromatograms of standards of known compounds and their RT values. So qualitative, it's correct this time. As long as, so you can compare your unknown to standards that you know, as long as the conditions are the same. So as long as all of these things are the same, you can compare the time that you have one molecule to the time of another molecule. But if they change, you can't say that you've got the same molecule because it has the same time. Okay. Sorry, this is taking forever. Okay, so quantitative example now, working out how much. So if we did, this is the example in your book. If you've got caffeine in an energy drink and you wanted to know how much caffeine, what concentration was in the energy drink, then you make up a standard graph with standards of caffeine. So amounts, concentrations of caffeine that you know how much they are. So if you used 0.1, 0.01, 0.02, 0.04, and 0.06 and ran those on a column and then measured the peak area that you got, then you could plot a graph of these. And then you put your energy drink in, your sample, and you measure the peak area and you see it's 3.6. So we need to plot a graph with our standards of known concentration. So x-axis is the concentration. So you put your 0.01 on and you have a 1 in this case the peak area is measured in millimeters squared. So your 0.01 microgram per mil concentration produces an area of 1 millimeters squared. Alright, so you go through and plot all of your concentration of your known concentrations, and then you get your sample of your energy drink and you see that it has a concentration of 3.6, so 3 is here and 3.5 is about there. So if you go across and go down, you see that that energy drink has a concentration of caffeine of 0.03 micrograms per mil for every mil of the energy drink. Alright, so if you drank a can of the energy drink, and I've just made up that a can of this energy drink would be 250 mils, so you've got a volume of it, and we've just worked out a concentration. I'm wondering if you can remember last year we used the equation. Concentration is the mass of your whatever it is you're studying in a certain volume. So this is our energy drink, and this is the caffeine. So if you wanted to know how much caffeine, what mass, you have to rearrange the equation. So take volume over the other side. We had 0.03 micrograms for every mil, and we've got 250 mils. So you can see that you cancel out the mils and you're left with the fact that you have 7.5 micrograms in that can of drink. Dilution equation. I wonder how many people remember the dilution equation. So if you took 20 mils of the drink first, and then you diluted it to 100 mils, how much would have been in that 20 mils if you've worked out the concentration in 100 mils? So C1, the concentration and the volume that you have at the beginning, equals the number of moles, and the number of moles of the caffeine. And the number of moles of the caffeine haven't been changed. They've just been, water's been added to them, so the concentration's gone down and the volume's gone up. Alright, so we want to know C1, the concentration in your 20 mils before you diluted it. So if you take this over the other side, B1 over the other side, then you've got a relationship between the 100 mils, the dilute 100 mils, and the concentrated 20 mils. So you can see that your original concentration was 5 times, 100 on 20 is 5, is 5 times more concentrated than the diluted one that you tested. So just keep an eye out that you've got these around the right way. You know, this should be a larger number than that if you had a concentrated solution. If you had, this was in your energy drink originally and then you added water. So the reason that you would do this is if your peaks are going to be off the graph. You can't read them properly. You can't, well, no, the reason that you do this actually is if on your calibration graph, if you measured the peak area and the peak area was up here, you would have to go across and extrapolate your graph, make the graph longer. And you can't make a graph longer because this graph might not be linear up here. So it might bend. So you can only use the graph between the highest and lowest point of standards that you've measured. So if it's too concentrated, if it was the peak was up here, it would mean it's too concentrated, so you dilute it to bring it within the range of the graph. There's been questions on that. Why do you dilute samples? Hopefully that makes sense.